talk about how to do regression with nonlinear functions, how we do that. So right now, everything we talk about here is linear combinations of the input features here. So even though in this case here, you're losing a two-dimensional space here. So the nonlinear combination, essentially your prediction here will be go along a plane here. And in a high dimensional space, that will be a hyperplane. And that will be the key characteristics of this type of linear combinations of features. But what happens, say, in our case here, your key model, your true models here, your hypothesis is not aligned. How can we handle that? And for instance, what happens if your true predictive functions here is a polynomial function, as shown in the right-hand side here? How do we come up with a model that can predict this type of nonlinear output here? So where we're doing this is this. We can transform your input features to include those type of nonlinear features. So the way you can do it is the following here. So for instance here, suppose your input data set here is X and Y, pairs of X and Y. But what you can do on the left side here, you can augment your features to include this quadratic features and also the cubic features here. Instead of using X as features here, suppose X right now is one-dimensional features here. Instead of using X here, you can also use X squared and X cubic and use these two additional features and include that into your input here. So as a result of that, your input here will include not only X, but also X squared and X cubic. So which means if your input data here is one-dimensional, after the transformation here, input data become three-dimensional, become R3. And which means that the model you have is going to be linear combinations of these three features here. The first is X, the second one is X squared, and the third one is X cubic here. And you have to learn the four parameters in this new cases here. And this type of techniques is called a feature transformation. So you start with the simple features here, but you can introduce nonlinear features through some predefined functional forms. So in this case here, you're using this simple polynomial functions here, up to order 3 here. So that's called a nonlinear feature transformation. So, so once you have these new features have been incorporated into your data sets here, in that case, your new predictive function will be a nonlinear functions of the X, because you do have this X squared and X cubic features there. However, the methodology we talk about for the linear regression can be similarly applied to this type of problem here. The only difference here now is that instead of one-dimensional features here, now you have three-dimensional input features here. And after that, everything, all the procedures stays the same, including how do you formulate your loss function, how do you learn the parameters of your models of that. So instead of learning two parameters, theta 0, theta 1, now you're going to learn theta 0, theta 1, and as well as theta 2 and theta 3. So you can see linear regression can be applied to learn those type of higher order terms, such that you can generate nonlinear predictions. So, so in general, for the one-dimensional features here, you can introduce this type of high order polynomial terms. You don't have to stop at the third order here. You can go beyond that, including even high order terms. Could be X to the power of 4, 5, 6 here. So that would be the higher order polynomial features you can introduce. So in fact, in general, you are not limited to only polynomial functions here. You can also introduce other type of functions here. For instance, you can introduce features to be 1 over X, right? And you can also introduce features to be square root of X. Or if you have high dimensional features here, suppose your input vector contains not only one X here, but also the first dimension is X1, second one dimension is X2. You can also take a product between the first dimensional features and then the second feature X2. So that would be the kind of a second order features, but it's kind of a product between these original two features of that. So the way, how do you introduce these features here is very generic here. It's all up to you in terms of how do you come up with a new nonlinear functional form to augment your existing features of that. So in general, the linear regression methodology we talk about here is actually a pretty powerful methodology. So the method here does not mean that your final predictive function is linear. It's only saying that we are using linear combinations of the features. The parameter space is linear because once you augment the features here, all the parameter is kind of still will be linear combinations of theta parameters with those individual features here. So linear regression is linear in the parameter space, not linear in terms of the predictive functions of that. Your function can be nonlinear in any arbitrary complex forms of that. So next I'm going to focus on using these polynomial features as an example. And it doesn't need to be that way, but I just want to use that as one way to illustrate some of the points, some of the things we have to pay attention to when we augment our input features to including those higher order nonlinear features of that. So I'm going to use that as examples of that. So now suppose say, well, I can kind of afford to introduce additional higher order features here through polynomial functions here. So let's use these simple examples to do that. So in this case here, I illustrate a few examples of that. Suppose this is my data sets here. This is a y here. This is the x in the original space. But now, after I augment my features to include x, not only x, but also x squared or x cubic or x to certain orders, to the ninth orders here, I can have learned the parameters corresponding to this additional features and then come up with a new predictive function. So that would be different result, different types of prediction function after you're doing the data feature transformation according to different orders of polynomials here. So in this case here, and your polynomial is simply a constant polynomial, which means that you are not including any features. Everything is simply the constant function that. And in that case, the predict function is very simple. It's a flat line. That flat line here is simply the mean of all the data sets you have here. So that will be the simplest possible prediction you can have. So next will be the original feature space. You do have x, and then your predict function is a line in this case. So you will learn both the slope of the line and also intercept of the line here. And that's the best fit you have. So next is this, including this second order features here. So you have x squared included in your prediction here. So now you have a quadratic functional forms here. That is your prediction of your regression problems here. And this is a high order polynomials here, including not only second order, but even higher order here. In this case here, I can include up to 9 orders of the input features of that. So that will be 9th order polynomial, and that's the learned best fit of the 9th order polynomial to your input features. That will look like something like this. So you can see that, so this higher order polynomials certainly fit the data better than lower order polynomials. And that's what we said again and again, right? So in this case here, this 9 order polynomial fit those training data more or less perfectly. And instead, in this 1 order polynomial here, you can see there's deviation between your prediction and observations here. So that's one observation we note here. However, the question is, how do we know which model is better? Among all the choices here, which one is better? So that's some of the questions we're going to talk about today. So this is probably related to the issues we talked about in the very beginning, the issues of the overfitting and the complexity of the models. The simple linear model, okay, this is simple, right? The high order polynomials is more complex models involving more parameters here. And in general, the more complex model can fit the data better than the simple models. As a result, you can see that they fit the training data much better than the simple models. However, and we said that repeatedly, what we cares about is the performance of the model on the test data sets, not on the training data sets here. So suppose now somebody provides you a new set of test data sets here, illustrated as this green dots in this diagram here, in this both figures here. So the green dots now are test data sets. You learn your parameters based on red dots, and then you evaluate your performance on the green dots here. So now you can see, compare the performance of these two models. So for evaluation purpose here, you can compare performance based on MSE calculation or some other criteria. But now suppose that you calculate MS a year. And now you say which model is better. If you look at these two figures here, you can see that for the linear models here, the MSE on the test data sets here is somewhat similar to the MSE on the training data sets here. And doesn't seem like there's a big difference between the training and testing MSE. However, on this right-hand side here, and you can see there's a big difference between the performance evaluated on these two data sets here. On the training data sets here, you can see MSE almost is 0 because the prediction overlap with the actual observation almost perfectly. However, you can do see deviations between the observation and prediction on the test data sets here. That's on the green dots here. And for some of them dots here, the deviation is very large here. And if you focus on these two dots here, you can see the prediction is way on down here. So I didn't even put on the figure. It's way down here. The actual observations here is along this side here. You can see the error for these two dots is actually very large, substantial, much bigger than the rest of them here. So as a result, if you calculate MSE for all the red dots here, so those overall MSE is going to be much better, much higher than the MSE calculated on the left side here. You can see that now based on this, you conclude that this ninth order polynomial is not doing better than those simple linear models. So this comes back to these curves we kind of talked about many times so by now. So this is called a, plot the performance of model on the y-axis and then plot the complexity model along the x-axis. So in this case here, the complexity you can think about is relate to the orders of polynomial functions you are trying to use here. The higher the orders of polynomial, which means that your model is more complex. So in general, we said the performance of your model will become better when you increase the complexity of their models because you have more freedom, you have more space to find the model fit to your data sets here. Because you have more space, of course, and as a result of that, if you are doing your training correctly, your overall training performance will become better when you increase the orders of polynomials. That was shown in this red lines here. So it will be monotonically decreasing as a function of orders of polynomial. However, this is not true on the performance on the test data sets here. As you can see in this case here, showing in this green lines here, your test performance, it will initially decrease as you increase the complexity of the model, but then after certain numbers here, and then your model performance will actually getting worse if you further increase the complexity of the model. You have, in general, you have this type of U-shaped curves that represent the performance of model on the test data sets. That is very similar to what we talked about previously, even for the nearest neighbor approaches of that. So, and then which means, because what matters most is the performance on the test data set. So ideally, we would like to choose the right orders polynomial along this point of that. So that would be the right one we would like to choose. And if we know the performance on the test data sets. However, in general, as I mentioned that, so the test data sets you should not touch your test data set when you try to come up with the best models. So we have to use cross-validation. So I'm going to mention that in shortly in the next few slides. All right. So before I do that, I just want to kind of mention this a little bit, kind of more or less theoretical foundations. People talk about a different way of representing this, study the relationship between performance and the complexity of the models. So alternative way is represented in terms of something called the trade-off between bias and variance. So usually that's another way when people talk about discussing the relationship between model performance versus complexity of the models. Right now we talk about mostly kind of underfitting, overfitting from this point of view. Alternative view is talk in terms of this bias, in terms of the trade-off between bias and variance here. I just want to mention that. So what does this mean? Right? So the idea is this, as I mentioned in the very beginning here. So whenever we try to come up with machine learning models here, we always have some assumptions put in the models. You have to start with some assumptions here. So those assumptions here in general may not be correct. Now that's fine, but we're trying to come up with assumption that is, reasonable and of course as close to the true model as possible. But on the other hand, and we want to make sure that the assumption here is not too complex, because otherwise, your data might be kind of overfitting your model stuff. So we want to make a kind of assumptions here, not too complex, but on the other hand, I want to make sure the assumption is close to your true models of that. So the bottom line is you always have some kind of bias whenever you develop your machine learning model, no matter what kind of machine model you are trying to do. Even for deep learning models, you always have some bias into your deep learning models as well, right? So some bias is always necessary for learning. The question is, what type of bias should I put into that? In this kind of discussion here, so we can think about it. So suppose you train your models here with different types of training data sets, and you're going to see, you want to say, suppose you present it with different training data sets here, how does model performance changes based on your different training data sets here? So let's illustrate it in these examples here. So suppose we're doing some regression problems here, and it's two-dimensional, and the black dots represent the entire space of all the dots, all the data you have. So that's all the entire space of all data you have on this problem here. However, in reality, you're going to be presented with a subset of this black dots. So for instance, represented by these blocks in this highlighted in red regions. And then I present those 1, 2, 3, 4, 5, 6, 7, 8 dots, eight points within the red regions to you, and you train your models. And then I want you to evaluate your models on the entire collection of data set. So that's the kind of test the performance of that. So now suppose, and you are presented with a different, randomly choosing a subset of data sets here. So I could choose subset randomly this way, representing the red dots here. I might well choose data in different selections of the 6 data sets here. That would be in this ones here, and this will be another choice of the training data set, 6 data sets here. So the idea is I want to see how does the model performance changes with respect to these 3 different training data sets here. Because that's very common, because somebody present you this training data sets here, those training data set is going to be a subset of the entire your space of data sets here. And the fact that you're presenting with the training data sets here might be those data sets randomly chosen for you. And for this application, you have this. Maybe for other time, somebody present you another data set of that. So the training data set you can view it as a sampling from the entire space of data sets here. So now in this case here, we have 3 collections of the training data sets. So now let's say I'm going to apply those regression models on these 3 data sets and then see what the performance look like. Okay. So now in the bottom row here, now I show you the predicted models based on 3 different polynomial orders here. The first one is the predicted models here, learned models based on the first order polynomial, essentially just constant functions here. And now I put all the 3 sets of training data set together here. So then, for instance, the blue lines here represent this constant I learned based on the blue training data sets here. The red line represents the constant I learned from the red training data sets here. You can see they are slightly different. So you can see based on the different training data sets here, your learned models will be different. So that's expected, right? So your model depends on your training data set. If you give me different training data set, the learning model will be different. So this is 3 different models learned based on the first order polynomial. That's constant function. So now I move to the first order polynomial. So this will be a line here, predict lines here. So now I have 3 lines based on the 3 different training data sets here. I have red, green, and blue here. So that would be 3 different models. And this is a 3rd order polynomial functions learned on these 3 different data sets. And you can see they give you different predictive models. So that's expected here. What I want to show here is that if you look at the three data sets here, you can see the performance of these models here. The models here are highly different based on what orders of polynomial you are using here. For instance, for the constant first order polynomial here, you can see even though the three constant lines are different, but they are not that much different. They are pretty much close to each other. This is not true for the third order polynomials here. And those orders polynomial are learned based on three sets of training data sets here. You can see the learned models here are very different here. And the first order polynomial sits in between. So they are different, but it's more different than the zeroth order polynomial, but less different than the third order polynomial. And we said that those models have high variance here, because depends on whatever type of data you are presented with, your predictive function here can be dramatically different. This is not true for this kind of lower order polynomials here. And even though you are presented with three different sets of training data sets here, and because your model is not so complex, the overall models here looks pretty similar to each other, which means that those type of models here have a low variance. So now essentially for different orders of polynomials here, you have these characterizations of the variance, predictive variance associated with the different types of models. The high order polynomial tend to have higher variance, lower order polynomial tend to have lower variance. However, there's another kind of attributes we need to think about here. This is the bias here. You can see that because the first order and the zero order polynomial here, they are more constrained than the third order polynomials, because you can think about it, they are a subset of the functional space of the third order polynomials. As a result of that, those models are more biased than the high order polynomials. So you can see final predictive testing errors is going to be always the error contributed by either caused by bias of your model or the variance of the model. So in fact, you can mathematically show that the predictive accuracy of your models, the errors here is going to be these two summations of error caused by two terms. One is due to bias, one's a term due to variance here. Whether your model is biased, of course, you're going to lead to high error in your predictions here. And however, if your model they have high variance, and that can lead to error as well. So that's always the balance between these two types of issues here. And this is something called a trade-off between bias and variance when you try to develop models of that. So this is a slightly different perspective. This came from perspective, say, if you are presented with different training data sets here, how does your, statistically speaking, do you come up with different models here? How different is your models? So that would be different way to present the same thing we talk about, in the context of considering the complexity model. How do we choose them here? All right. So given those considerations here, finally in practice, right, in the end, we have to determine which orders of polynomial should I choose. So that's kind of fundamental task we have to decide to do. And what we do typically is we're going to do evaluation purpose, evaluate the performance on holdout data sets here. And then we're going to test different models based on training and then evaluate those on the test data sets here. And then this is also very commonly done in many competitions, including the Kaggle competitions. If you want to participate in the Kaggle competitions, I mentioned that. So usually, somebody will provide you the training data set, you train your models. And then in the leaderboard, you have this validation data set can evaluate your model. And you can select your models based on results, on the leaderboard results there. And finally, they have some data set called test data set, and we evaluate your finally selected models. So that would be a way to detect overfitting or kind of control and choose the right complexity of your models here. So right now, the question is how do we choose the right collection of models here? And then also they relate to, overall, how many data you should use. You have to think about, is this data sufficient for this amount of complexity on the models I'm choosing here? So there always is this relationship between the two here. There's no fixed formula for choosing the right models. It depends on the amount of data you have, the characteristic of your training data set you have here. So one way of doing this is doing this cross-validation, right? So that's what we talked about last time here. Suppose you have this training data sets here, what you can do, because I don't want to touch the test data set. What you can do, you can split your training data set into some into your model parameter learning and the rest of them for kind of model complexity and determination, choosing the right model of that, split them. And not give you one way to fairly choosing the right models of that. For instance, you might want to say, even though I have this entire training data sets here, I might split them such that I have some of them here, I use that for learning the parameters of my model. And for the rest of them, highlighted in the green regions here, I use it for evaluating the model, different types of models with different polynomials here. And then for that purpose, I'm choosing the right one of that. So it's for the validation purpose of that. So the most common way of doing this ones here is using something called a cross-validation. The reason is this: if you split your model, split your data in a fixed scheme here, say, well, this data set here, I'm going to use this for training, using this for validation here. So what happens is this? Well, if you think about it, I'm evaluating the performance of the model based on the 3 data sets here. You can see if I only use 3 data samples to evaluate the different types of model, you can see, I don't have enough data to have confidence in the evaluation purpose. I have confidence to say this is the correct model of that. Ideally, you would like to use more data to evaluate your models. So that gives you kind of, your estimation is going to be more accurate. So the question is, how do you utilize more data for evaluation purpose? And the way is doing cross-validation, as I mentioned previously, right? So the way you can do is you split data sets into k disjoint sets, and you hold out one set for evaluation, and then you will train on all the other data sets, essentially k-1, so all the remaining data sets of that. So for instance, in that example I have here, you can do k-fold cross-validation. So that would be 1, 2, 3, that would be 3-fold cross-validation. So this is the first fold here. So this is your training data sets here. And you learn the parameters of your model. Suppose I'm going to learn the linear regression first order polynomial first. You learn that parameter, 2 parameters here based on these 6 data sets. And then you evaluate the performance of these models on these validation holdout data sets here, and 3 of them here. And you calculate your MSE. So this is the MSE based on the first split here. And then what do? You go to the next split. So next split will be, you leave the middle 3 for evaluation and the other 6 for training purpose of that. So highlighted in this curves here. So this is 3 for evaluation, the red for test for training. And you learn a new line here. So the slope and the intercept line will be slightly different from the one in the first split here. Once you learn the line, and you can evaluate, calculate MSE on these new 3 training validation data sets here. So that gives you a new MSE. So this is MSE came from split 2, and finally you proceed to the final split. That will be split 3. So split 3, you use the top 3 samples for evaluation, the bottom 6 for training. So you get a slightly new lines here and learn the parameters, and then you calculate MSE. So by doing this k-fold cross-validation here, you will learn 3 different models here, all based on linear models here. And then as a result, you will get 3 different MSEs. So that is the evaluation based on this data sets here. And then what do you do here? You're going to average these 3 MSE here to get a 3-fold cross-validation. You can sum, no, it's not average here. You can sum them here or average, and you can do either way. You can do average here, right? You can average them here. You get this 3-fold cross-validation MSE here. You get this number here. And this tells you the MSE on for your linear, first-order linear models, right? So something to keep in mind here. So this MSE here is not calculated based on single model, but instead based on 3 different models trained on 3 different data sets of that. But however, this MSE is meaningful because it tells you, it's saying that if you use linear regression, what is the expected performance of the first order linear regression models of that, right? So it provides you some guidance. Say if that's for the first order polynomial, I would expect that overall MSE is this. Another benefit of this MSE here is that it's more accurate because it is MSE based on calculus now over the entire data sets here, because the split here is based on first three, and the split 2 based on another 3, split 3 based on the third 3 sets of training evaluation data sets here. You can see overall the MSE finally here is evaluated on the entire 6 data sets. So the 9 data sets here, 9 samples here, not 3 samples, but 9 samples here, because of these reasons here, I might believe that this type of evaluation is more accurate to reality, right? So now you do this for your alternative model. And suppose I'm doing this for your second order polynomial functions here. So in this case here, you need to learn 3 parameters instead of 2 in the previous case. And again, you can apply the 3-fold cross validation. So in the initial split 1 here, you have 3 validation data sets, and the remaining 6 for training. You learn this quadratic functions here because I'm using second order polynomial fit. And then you calculate MSE once you learn these lines here. That's MSE from the first split. Similarly, you can calculate MSE from the second split and the third split. And then again, you can average to calculate the mean MSE from the 3 splits. You get a 3-fold cross-validation MSE on this based on the second order polynomial fit to this data sets here. That's this one's here. So now you compare these numbers to the previous number you have here. So previous you get 464.1 for the first order polynomial, but now you get something much higher. And then you can conclude that, well, based on my cross-validation methodology, I'm going to choose this first order polynomial instead of the second order polynomial here, because it gives me the lower the cross-validation MSE. So I have reason to expect that that model would tend to be doing better on test data sets than these high order polynomials here. So that's a very common procedure for choosing different models. I'm using this kind of cross-validation procedures for choosing different types of models. And in this context here, is choosing the orders of polynomial functions. All right, so that's about it. This is something called a cross-validation here. So the advantage of this cross-validation here is so it allows you to use more validation data sets instead of fixed split of in the scheme we talked about. If you split them and use a fixed training and validation, in that case, your overall evaluation is based on only 3 data sets. But now, if you're using cross-validation, you essentially can use every data samples for validation purpose of that. However, there's disadvantages here. So really, there are more work here. You have to train K models instead of just 1 model. So that's more work to do. Then secondly, and another thing you have to keep in mind, the evaluation is done on 3 K different models. This method here does not give you a single model because you learn K different models here based on K different splits. So as a result that, so the MSE you calculate here is not evaluating any particular predictor here, but it's kind of aggregate, average result predictor. So that's something to keep in mind as a caveat with this type of models here. And then, and there are another disadvantage here, essentially your training performance, your training is still done on kind of, not on over entire training data set, but on a smaller number of training data set you have. So that's a disadvantage here. And so that's keep in mind here, essentially you lose some of the data in the training.
Professor, I had one question.
Yes.
So from this, from what I understand, you are trying to say this helps us identifying what order of polynomials is useful for our model, right? Like in the previous example, the second order or third order polynomial was not, it had a higher average error, the k-fold error compared to the first order linear model. But, and as you said that the final k-fold validation value is not for a particular model, but it is like the average of all. So then if we run this experiment and we figure out that a linear model is better, how to select a particular model out of those linear models?
Right. Yeah, so that's a very good question, right? So he's asking here, because if you go back here, he's asking these questions here. So in this case here, in the k-fold cross-validation, so I came up with 3 different models here. And then in the end, I determined that this model is good. It's better than the second order polynomial. So in the end, I determined that first order polynomial is a good choice for this type of data sets here. And but now, suppose you're participating in a challenge here, you still need to come up with the 1 models for making predictions on the test data sets. What should you do? Well, typically what people do is this. Once you determine that the linear models, first order polynomial is the right choice, and then you're going to retrain your models using the entire data sets here. So that'll give you kind of a better fit of the parameters in the model. So essentially, these procedures here, the cross-validation procedure, only provide you a way of choosing the types of model you have. However, once you determine that this is the right model I'm going to use, and then you can retrain the model using the entire collection of data sets. So which means that the final learned models here will be different, slightly different from any one of them here, but hopefully can fit the data better than because you are using entire collection data sets for learning purposes. So that's a very common way of doing this.
Okay, thank you.
Yeah. So in general, what we want to do is we often want to monitor the performance of your model as the number of data sets you have. Because often somebody will, when you try to solve any particular problem, and people will always ask you, well, should I go collect more data? Is this data sufficiently large enough for me? And this is always a very hard question to answer. Like somebody say, well, I have this problem here. Tell me how many data I need to collect in order to come up with a relatively good predictor. So that's in general, it's a very hard question, but people will ask you very often in practice. How do you do this? Well, the way we do this one's here it is. So often that you're going to plot this type of learning curve. So the learning curve plots the performance of your models as the number of training data you have, essentially the training data size, number of training samples you have in your models. And then of course, when you increase your training data size, your cross-validation MSE will tend to become better, right? So your MSE become lower. So because I plot the 1 over MSE, so that which means your performance, your model performance will get better when you increase the number of training data sets here. And so usually you plot these curves here, and then you see how the shapes of the curve look like here. So if you, right now, if somebody give you the number of training data located in this range here, and you know right away you're saying that, well, you need more data. And because more data will provide you a bigger room for improvement. And then you go collect more data, and now you go in this phase, and you do this analysis again, you say, well, so now it seems like I still have plenty of room for improving the performance if you give me more data, if you keep doing that. And however, up to this point here, the benefit of collecting more data, it diminishes. And you don't see more benefit there. And many times here, this function will gradually saturate. And after that point here, essentially saying that, well, the more data doesn't really help you. I already learned enough statistics from the data sets here. And then essentially, that's it. You're done with your problems. So this is the right number of samples to use. So this is a very useful in practice to monitor the performance of your models as the number of training samples you have here and see how these curves look like. And is this going to reach the plateau, and then you'll be happy. Otherwise, which suggests that you will need more data to train your models. All right, so I mentioned this k-fold cross-validations here. So one disadvantage of the k-fold cross-validation is this. So every time when you train your models here, you are using 6 training samples here instead of entire 9 samples here. So ideally, the more training samples you have, potentially you can learn the parameters better. And so that's the kind of and the trade-off you have to think about here, right? How can I use more training samples here? Well, there's one extreme case here is something called a leave one out cross-validation. So in that case, you're going to split your data sets into k exactly equal to the number of samples you have. So which means every split here, you're going to use only one data for evaluation and all the rest of the data for training here. So that's kind of extreme case of the k-fold cross-validation. And so in this examples here, so this is the first split here. I have this remaining data for training, the first data for evaluations here, illustrating this part of that. So the benefit of this project here is that you do have more data for learning parameters in your models. And by doing that, you're hoping that the parameter you learn is better, is more accurate. And then you evaluate performance on this one data set here. And you cycle through them here, just like what we did for k-fold cross-validation. And then in the end, you average the MSE calculate, you evaluate on the single dots here, you get this so-called leave one out cross-validation MSE. So that's an alternative approaches, and so for model selection. And so in this case here, you do have an advantage that you are utilizing more data for training in each split. But however, you do have a disadvantage. So disadvantage here is this. So in each split here, you evaluate your model only on one sample, okay? So when you evaluate from on one sample, you know that that evaluation is not going to be accurate because it could be biased. Could happen this there is just somewhat to be an outlier here, and as a result, no matter maybe your model is correct, but because you have only a single data set here, your evaluation here might be very biased. So that's the disadvantage of this leave one out cross validation here. So your overall final cross-validation MSE may not be as good as k-fold cross-validation. So this is the trade-off you have to think about here. If I use k-fold, let's say 10-fold cross-validations here, or 3-fold cross-validation in the example I show you. So you have less data for training, but you have more data for evaluation. So you think that your evaluation performance is somewhat better. And on the other hand, for the leave one out cross-validation here, you have more data for training, but you have less data for evaluation. So it's always the balance between the two. So however, and there is some theoretical work and demonstrate that leave one cross-validation is actually not a good methodology. So there is a fundamental flaws in this methodology. So in general, so you don't have to use this one here. In general, maybe you're choosing the correct k-fold cross-validation. In practice, many people are choosing 10-fold cross-validation. If you have 100 samples, you're going to use 90 for training, 10 for evaluation, or using kind of 7-fold cross-validation and so on. So there's always this kind of balance between these two here. So, so this leave one out cross-validation sounds like it's good, but seems like there's a potential bias in the finally calculated the MSE cross-validation MSE. Okay, so these are possible choices for model selection based on cross-validation side of that. So you can choose either leave one out or k-fold cross-validation by choosing k here. Right? So that's what I would say regarding this kind of nonlinear features. So, repeat what I just said here. So the linear regression is only linear with respect to the parameters here. And you can come up with the nonlinear predictive models here by incorporating those nonlinear features. And so in the class, we talk about the polynomials, but in many cases, and there are lots of other type of nonlinear features. And in many cases, like radial basis functions, even neural nets, right? You can use, and then there is actually, before this modern age of the deep learning here, there is something called a random neural net. So random neural nets, what people do is this. You randomly initialize the weights of your neural nets, and then you use X as input, and then come up with this output here. And then you use those random neural net produce output as your features. And then you retrain model based on those guys here. And then suppose you initialize your neural net with many different initialization, you can come up with many different types of features of that. So as a result, that this type of features can be used for learning for linear regression models as well. It turns out that works fantastic, very good. So then if you go back historically, that turns out to be very good methodology. And of course, there are also many other features people have talked about over the years, especially if your data is structured data. For instance, if you have images, or if you have sound waves, as your input. For instance, the auditory input, right? Sound wave as the input here. And what people typically do is to apply a Fourier transform of your kind of sound waves to generate the scores in the spectrum across different frequency spectrum, and use this kind of spectrum as the input features. So that you can imagine is also kind of a manually generate features by applying Fourier transform to your input instead of simple polynomial functions there. So there are many different ways for feature engineering, for transforming the features, for augmenting features here. And in fact, that's a lot of work has been done in this field before the modern era of deep learning. In the old days, people spend a lot of effort to say, well, this is the better way of coming up with the correct features for this particular problems. But of course, nowadays, people tend to do less on this type of work anymore because and they believe that if I apply kind of the deep neural nets, I can learn these features much better than kind of develop these features manually. All right, so this is some historical reasons for that. Okay. So next, I'm going to talk something. The remaining part for the linear regression is something called a regularized linear regression. Let me go through that part of that. So this is also related to the problem of how do you address the problem of overfitting versus underfitting here. So I mentioned that, so you always see this type of curves of that, performance of your model as a function of the model complexity here. So right now, if your model is overfitting, say suppose you have using the higher order polynomial functions here, and then your order's polynomial is way too high, your model is too complex for the data set you have. And then so far what we're doing is saying is, well, you should decrease the order as a polynomial. Instead of using ninth order polynomial, let's reduce them to the first order or second order polynomials. Effectively, by doing that, what you're doing is you're removing some of your features. You think about this way, right? Suppose now I already transform my features to up to ninth order polynomial. I have x1, x2, up to x9 here. Those 9 would be high order features for that. And because of what we just talked about here, because we say that model is too complex. And then what you need to do is to reduce the number of features, remove some of these high orders for that. And so that's something that's very common in the machine learning, is a task called a feature selection. And how do you, maybe, you have 9 features here, maybe there are only 3 features are important for building up these predictive models here. Remaining features are very noisy, they are not predictive. But because you are introducing them, including them in your input data set, you have to learn something. You might be overfit on this type of noisy features. So of course, the better way is just try to throw away these features, right? So that's the one way of dealing with these questions. The question is this: how can I decide which feature should I keep, which feature should I discard? And that's something called a feature selection here. And that will be used to decrease complexity in your models. So there are multiple ways for doing this, and you can cycle through all each features here, and then use cross-validation to determine which feature you can throw away, which feature you can keep. So that's one way of doing that. That's more or less the one we just talked about here, using cross-validation to determine the order's polynomial. So there's an alternative ways for doing this is through the framework of so-called regularization. So the motivation for this, and suppose, again, within the context of the polynomial function fit to this regression problem here. Suppose there's a real lines here. Now if you use 0 order polynomial, you get a constant here, and a first order, and third order, and the ninth order here. You can clearly see that for 9 order polynomial here, it's the model is too complex for this data set you have here. You are overfitting your data sets here. And the question, how do we handle that? Well, so one interesting observation is this: suppose you apply this different ordered polynomial functions here and on this data set, and then you observe those learned parameters. Those are coefficients. You learn based on different orders of polynomial here. And if you show them in this case here, they will look something like this. It's very common to look something like this on here. So again, this is this is a zeroth order polynomial. Essentially, there's only one constant term, right? And that's the constant term you learn. That's the theta 0. In the first order polynomial, you learn theta 0 and theta 1 here. So that is the coefficient corresponding to your feature. In the third order, you have theta 0, theta 1, theta 2, theta 3. So the final one is the coefficient corresponding to the third order x cubic here. This is ninth order polynomial. Coefficient correspond different polynomial orders. So this is what you see. What you notice from this table here is this. You will see something striking is that those coefficients becomes enormous for those ninth order polynomial functions here. They have extremely high coefficients here. The reason why you need this, why you come up with this high coefficient here is when you do ninth order polynomial here, because the function is trying to fit this training data sets, try to fit in reduced MSE. So you have to kind of twist your kind of this high order, this polynomials twisted around here. In order to twist around, you can see that the convexity of your function here is very high. So which means that the terms, those coefficients in front of your high order terms here is very large. So that's the reason you can see there's big coefficients corresponding to the high order terms in your polynomial functions of that. So the question is this, well, this sounds like whenever you see apply any kind of machine learning algorithm, you see those coefficients here, some of them are enormous. So that's suggestive of something that your models are potentially overfitting your data sets. And how do we handle that? Well, maybe one way of handling this is this. Let's add some constraints into my model to constrain those parameters not be too large. Enforce them, say, and within a certain range as small as possible. And so that eliminate this type of possibilities. So the way of doing this is using the framework of so-called regularization. So in the framework regularization is this. I'm gonna add one additional term into your loss function. So remember that suppose this is my loss function for the linear regression here, and this is the MSE loss, mean square error loss we talked about previously here. And the notation here is slightly different. In general, I like to put x to be x transpose, x times theta instead of theta times x transpose here. So you can think about this as the MSE, the error term data loss here. And then what I'm going to do here, in addition to MSE loss, I'm going to add one more term. So this is this alpha to be theta transpose. Essentially, this is the squares of the coefficient, summation of the squares of each individual coefficients. And so this is also called the norms of this vector theta, L2 norms of this vector theta, or more commonly choice is called Euclidean norms of these vectors. The square of the Euclidean norms of that, the square of the Euclidean norm is simply summations of squares of each individual components of that. And so I'm gonna introduce this additional term into my loss function. And then so once I do that, and let's see how does this impact my final result. Well, because I introduced this kind of penalty term into my loss function here, when I minimize my loss function with respect to parameters here, not only I need to minimize the first terms here, that's called a data loss terms here, I also need to minimize this regularization terms. And how do I minimize this regularization term? I want to make sure that each individual theta is small. And that's how do we enforce that learning algorithm to make sure that the learned parameter is not too large. And then so in the end you have these two terms. So this is the MSE loss, this is the penalty terms here. And sometimes we need to balance the contributions of these two terms to the final loss function. So that balance is introduced through these parameters here. This is called an alpha. It's called a regularization parameter. This is simply a number, a scalar that is given to you. You have to set this number before you carry out this learning process. So you can think about it as a hyperparameter. So you have to choose before you learn the parameters of the theta here. So essentially it's given to you here. You set this alpha to be certain values, for instance, 1 or 0.1, okay? This is called a regularization parameter. So this regularization parameter balances the contribution of these two terms here, and then the final theta here what depends on this alpha here. And And if your alpha is too large, right? If your alpha is too large here, which means that this penalty terms weight more than this data loss term on this loss function here, which means that I should try to minimize these terms first, or more, right? Because the weight here is too large. So which means your theta would tend to be more close to 0. On the other hand, if alpha to be very small, and that means the penalty term matters less to the overall loss function, which means your theta will be close to the original loss, learned loss based on purely based on this MSE terms here. So you can see the balance of these two here. The higher the regularization parameter alpha, in general, the smaller the values of the theta. So what I'm going to talk about, how do I choose the correct regularization parameter? But for now, I just assume that the parameter is given to you. Okay, so this is something called a shrinking problem here. Essentially, by introducing these regularization terms here, you are shrinking your parameter toward 0, more close to 0 here. And so let's see how does this regularization term matter to results here. So without any regularization, which means if you set alpha to be 0, and you can see that, you learn, suppose I'm going to apply to the 9th order polynomial here. That's the 9th order polynomial. I learned that as a result of that, you're going to see large coefficient corresponding to higher order terms. Now, if you add certain amount of regularization to alpha here, suppose alpha equal to 0.1. I just use that as an example here. So now you can see now your higher order polynomials, because those higher order coefficients are pushed towards zeros, you can see your predicted function tend to be more smooth than the previous ones here, and the plot to be look something like this. All right, so that's for moderate values of regularization. So you can think about alpha equal to 0.1. So now if you choose alpha to be very large, say if you choose alpha to be 10, the very large regularization. And because I said that because the penalty term weight more on the loss function, as a result that you push those parameter theta more towards 0. And then to this extreme case here, most of the parameters are all zeros, which means in the end, you only have a constant function, more like constant function here. You have less fluctuation around these high order terms of that. You can see the more regularization you put, the function more tempted toward this kind of constant functions. All right, the question, you can see that regularization terms have a big impact on the functional predictive functions here, learned predictive functions here. And the question is, how should I choose this regularization term? So the methodology, you're going to use this cross-validation. So you're going to use learning those parameter alpha here based on cross-validation, just like what we did for choosing the orders of the polynomials here. So the way you do, you test a few different choices of the alpha here. In this case here, alpha goes from small values to higher values here. And the plot in this case here to be the log of the alpha, but you don't need to be log of the alpha here. Essentially, you can imagine alpha goes from close to 0 to very large values here. And as a result here, the more alpha you choose, the bigger alpha you impose on the regularization terms here, you can see that your training performance is getting worse. The reason is this, because the higher the alpha, the higher the penalty term. And because when you impose a penalty term in your loss function, you're trying to minimize not only your fit to your data, but also try to make the parameter smaller. So as a result of that, your training error increases when you increase the regularization parameter. And which means that if you go from left to right here, your model become less and less complex because more regularization was imposed on your models here. And however, on the other hand, the test performance can show this type of a U-shaped in the curves here, and not too large, not too small, not too large, with certain sweet spot here, with the right range of the alpha, give you the best testing performance. And that's the lowest point on the test performance is the right alpha I should choose. And then you can choose based on cross-validation procedure for doing this ones here. So, so this shows you some of the real numbers. If you apply to the problem I just show you here, for 0, if regularization parameter is 0 here, this is the parameters here, show larger values. If the median, this is the values here. If alpha is too big here, and this too big is also not good because your model becomes too simple because you push everything towards 0. and then you are underfitting your models of that. Certainly, that's the right range of the parameter you would like to see based on this data sets here. And that's what do we see in this case here. So this alpha 0, you can see where you have a higher order polynomials here, you tend to have in a large errors on the test data set. But if you add certain medium levels of regularization, so now you can see that the curves become similar, and also the performance on the training and testing become closer as well. Right. Let's go back here. So this regularization terms right now I talked about here is something called a L2 norm regularization. So because in the penalty term here, I take the square of the square of each individual component and then sum of the square of each individual component. But that's only one possible choice of regularization function. In general, there are many other choices of regularization functions here. So most commonly, the choice of regularization function is something called an LP norm. So I don't know if you remember from your linear algebra class, the norms of a vector can be defined in multiple ways. So then the most common ones is this L2 norm, is this Euclidean norms, and we just talked about here. But there are many other types of norm. So in general, there's something called an LP norm. So in calculating LP norm, you do this. Take absolute values of each individual component, take the power of p, summations of them, and take the square root of 1 over p here. This is something called an LP norm. This norm is valid as long as your p is greater or equal than 1. So then this will be a valid norm function. And the LP regularization, essentially you can use any p-values as long as it is not less than 1, and use that as a regularization terms. So now will be all kind of a valid regularization terms. So that all of them will push theta towards 0, but in a different fashion, different manners of that. So the most common choice of this regularization terms here with p choosing to be either 1 or 2. So when p is equal to 2, that's the Euclidean norm we talked about here. And this plots the so-called isosurface. Essentially along the circle here, the norm is equal to 1 here. This norm is constant for the two-dimensional theta 0, theta 1 here. But if you are choosing this p equal to 1 here, and this is something called an L1 norm, and the isosurface for the L1 norm is this kind of diamond shape instead of a circle here. The reason is this: if you go along this lines here, you can see that if you add up this x theta 0 and add up to theta 1, they equal to 1. And as a result, that you have this diamond shape as to be the isosurface of the L1 norm versus the circle for the L2 norms. And these are the two most common choices of the regularization functions of that. Of course, you can choose some other of that. So this is not norm anymore. This is the case if you choose p equal to 1/2 or look something like that. So however, most of the time, we're going to focus on these two here. And this is when p equal to 4 here, then what this look like. All right, so in terms of the functional form, this is in one-dimensional space. This is what look like here, right? So the ones I show you here is the isosurface in 2 dimensions. In the one-dimensional space, that would be look something like this ones here. This is the p equal to 2 here. That would be simply equal to x squared, right? P equal to 2x squared. This is the when p equal to 1. That's simply equal to absolute values of theta here, and this is the other forms of that. And so you can see they have slightly different forms of that. This guy here is actually problematic here because this function here is not smooth, not differentiable at origin. And this is Euclidean norm here is differentiable. It's very nice, but this one is not differentiable here. And in fact, that can cause some issues. But in fact, it's exactly this kind of non-differentiability and lead to some of the popular applications of this so-called L1 norm-based regularizations. So the reason is this: the difference between this L1 versus L2 is the following, illustrated in this picture here. So now suppose I'm consider the simple line fit here, two features here as a result of 2 parameters. One is theta 0 and theta 1. So this is a contour lines of this MSE function, right? So the MSE, I remember we told you that it's a quadratic function. Suppose this is the contour of the MSE. This is the center of the MSE. This is the optimal point without any regularization. Right? Without any regulation, the optimal theta is going to be center point here. But now, if I add this regularization terms, L2-based regularization term into my loss function here, and then I have to balance these two type of loss here. So the L2 norm say I have to shrink this toward origins here. The MSE said I have to shrink toward, I have to, I have to converge toward the center of this contour lines here. So you see these two objectives are very different. You have to strike the balance between these two here. So suppose, in general, it's saying that suppose I constrain that my regularization term has to be at least no greater than the circles here. So you say among all the circles here, I find the best theta that minimize my MSE. So among them, you can see this is the point that minimize the MSE because the touching between this pink regions and this contour lines here, and this is the minimal point solution to that. This is towards zero, and now the solution to that. So this picture will be different if I use L1-based regularizations. And if you are L1-based regularization, this isosurface look like a diamond here, right? Now you can see what is the intersection between the diamond and the contour lines of the MSE function. You will see that the intersection point is always along the axis of these parameters here. They're not going to be in the middle of here, but it will be located exactly along the axis here. So what does this mean? The means here, the optimal solution means that in this case, theta 1 will be exactly 0. And theta 0 is not 0, but theta 1 will be exactly 0. And that's a very common characteristics of the L1 norm-based regularization. So which means that if you apply L1 norm-based regularization into your loss function and you try to find optimal parameters, very often you see that the solutions of your problem here, you contain a lot of coefficients that they are exactly 0. They're not simply small, they are precisely 0. The reason is this exactly because of this, because their isosurface look like a diamond instead of this smooth surface as in the case of the L2 norm regularizations. So that is exactly the reason that why L1 norm regularization becomes popular, because if you identify those coefficients corresponding to some features to be 0, and you know immediately that those features are not participating in my predictive functions. And as a result, you can simply throw away these features. And which, in other way, is saying that you can select features based on the learned result, based on the learned parameters of this models here. You're going to use only features with those thetas are not 0. If those theta sub i's are 0, and you can discard those features because they are not informative for your predictive functions of that. And so hence, this methodology not only provides you for regularizing the complexity of models, but also for provide you a smarter way, automatic way for selecting the features of your input data sets of that. So this is different from L2 norm regularization. L2 norm will push all the parameters towards 0, but they are making it small, but it will not be exactly 0. So as a result, that you can still don't know which one should I use, which one should not use. So you can see some of the advantages of this L1 norm-based regularizations. Well, the question is this, and how do I learn the parameters model once I have this regularization terms? Well, you can apply exactly the same methodology of the gradient descent methodology for learning the parameter of the model. The only difference now is this, in addition to the calculate the gradient respect to the MSE loss function, but you also need to calculate gradient respect to this regularization terms, right? And so that gradient can be calculated. So I illustrate in this part here, right? So in the one-dimensional space here, suppose for the L2 norm-based regularization, the gradient of the L2 norm regularization is simply to be a linear terms. And essentially, if you think about it here, if you have theta square, a derivative of theta square is theta, 2 theta. So that's the reason you have line terms of that. That's the gradient of this regularization terms, the L2 based regularization. For the L1 norm-based regularization, the derivative is slightly different here. And this is in one-dimensional space here because it's simply the absolute values of the theta here. You can see is that in the negative side along these lines here, on the positive side along this line at origin, the function is not differentiable. And as a result of that, the gradient will be exactly the one, constant one, sorry, this is negative of the gradient here. Negative of the gradient will be positive 1 along the left side and negative 1 on the right side of that. So that plot in the red lines here to be the negative of the gradient here. You can see it will be constant function. At origin, the gradient is not defined, can be 1 or -1 here. In fact, you can plug in any values of that. And it turns out it doesn't really matter that much for optimizing, for learning the parameter of the function. However, because of this, at this point here, the gradient is not exactly, does not exist. And people, strictly speaking, call this type of gradient called a subgradient to distinguish that, the fact that this function is not differentiable. But however, the gradient is very well defined in either this left side or the right side. It's just that at origin, it's not defined of that. So once you know how to calculate gradient here, you can simply apply gradient descent methodology for learning parameters in the models of the function. All right, so that's called regularization-based framework for controlling complex models here. It's very generic. People use it all the time. And as always, you should think about once you learn the parameters here, maybe you in order to kind of ensure that your model can generalize well. And if you're thinking that you are overfitting the model, you are overfitting your data, the one thing you can do is say, let's add a regularization term to make sure that the model can generalize well on the test data set. So in terms of terminologies here, the L2 norm-based regularization, and people have named something called rich regression. When people say, I'm going to apply rich regression, what they mean is this, they're going to use this MSE loss and plus the L2 regularization to learn the parameters of the model. On the other hand, if someone say, I'm going to apply loss-su regression to learn the parameters of the model. So what they mean is that they're going to use MSE loss and then add this L1 norm-based regularization on the loss function. And hence you have two different names. But then what they mean is that they apply these two different types of regularizations on the loss function. All right, so that's it. What I want to say regarding this linear regressions here. You can see, linear regression is a very powerful methodology. And in fact, the reason we spend a lot of time talking about linear regression here is because later on, many of these other methodology, and even for classification, for the neural nets, all based on the fundamental ideas of linear combinations of features. But the only difference for the neural nets is they're going to apply the linear combination repeatedly, multiple times, and in multiple layers of that, and then make it more complex. But the fundamental building block is this linear combinations of features. So as a result of this type of foundation here is very important. And however, once you understand this, later on in the other part of that, it can be relatively kind of easier to understand. All right. So that's for the linear regression part of that. So then my plan is this. So next week I'm going to talk about the classification problem. So far, I talked about regression problems, and I'm going to simply apply similar methodology, a linear model for classification problem. So that's the goal of the next week. So let's see, I still have a couple of minutes here to see if you guys have any questions.
Professor, I had one question.
Yes, go ahead, please.
Yeah. In the previous slide where you had shown, So you mentioned that because of the regularization term, we will only be picking a solution that is in the region highlighted in red, right? So what is the radius? So for example, what is the radius of this particular circle, and can we have control on that?
Okay, that's a very good question. Very good question. So I kind of skipped through this quickly here. So the problem I missed, so I can explain more in the next lecture here. So right now, the framework I talk about here is this. So I have this minimize my MSE plus this regularization terms, alpha times this guy's here, okay? So equivalently, I just say equivalently, this problem can be formulated as something like this. Minimize these guys here, subject to constraints, this regularization, this term here is less or equal than certain values. So I call that beta, okay? So that would be alternative formulations of this problem here. So that would be very close to this picture representations of that. And essentially saying, well, I want to minimize my functions of the object functions, the MSC function here. At the same time, I want to make sure that my parameters here are located within the range around within this isosurface here. And the question is, how large is this radius of this isosurface? So that actually depends on the regularization parameter alpha, okay? So you can imagine that if you choose alpha to be very small, let's say alpha to be very small, you think about in the extreme case, alpha to be 0. So which means that if alpha is 0, which means you don't impose any regularization term. So in that case, your radius is very large, okay? Covering entire region. Essentially, you are not imposing any constraints here. On the other hand, if your alpha is very large, very big, which means you are imposing a strong regularization, and you're going to shrink this isosurface radius here and make it smaller. And you can think about it, shrink it and make it smaller. As a result, that your learned parameter has to be the isosurface, the contour here, touch this smaller isosurface. That solution will be further away from the center of that. So yes, so the question, your question here, so answer your question here. So the radius here, what depends on the regularization parameters here. And in fact, I do not have a fixed formula for doing this. However, there's a one-to-one correspondence. If you know, give me alpha here, there's corresponding to radius constraints on this isosurface here. So that is related to how do we formulate this kind of a constraint optimization problem there. So if I have time, I can spend more time talk about it in the next lecture. But that's roughly the idea behind it.
Thank you. And I was also wondering why in the previous example for the L1 regularization term, you mentioned that the loss function will always be in a corner, but could there be a particular loss function wherein it is not in the corner?
Right. So so in general, right, so this is only kind of two-dimensional space here. So the reason because this is the function here, I have this particular corners here. As a result, and this can be shown, can be proven that as a result, the optimal parameters of theta, if you impose L1 north here, some of them will be exactly 0. And what 0 means they are at the corner of these functions of that. So that you will not have optimization center in the middle. Well, it's possible in the middle for some of them, but it's also, so you could possibly in some point here, right? It's possible here. But in general, you might touch corner in a high dimensional space. So what I mean here, in the end, your parameter here or some coefficient will be precise to 0. In fact, depends on your regularization parameter. The higher the regularization parameter, the more theta sub i's will be 0.
Okay, thank you. I think this refers to the linear programming law that states that if we are trying to minimize or maximize a system of linear equations, we find the feasible region and the solution optimal will be in some corner. Is it like?
So, yeah, and I understand what you're saying. I think it's not exactly the same because in that case, in linear program cases here, because you know that your constrained surface is a geometric structure, and you know the solution in the corner of that. In these guys here, right now, when I formulate as the regularization terms here, I do not have a specific geometric structure. However, if I impose these guys here as a constraint, if I reformulate the problem as I just mentioned at the very beginning, so I'm going to minimize the MSE subject to these L1 norm constraints, and then in that case, you can see that your constraints here, it turns like to be more like a kind of geometric structure. You have corners, and then the solution is going to be in the corners of that. It's related, but it's different from the linear program in the sense that your objective function in this case here is going to be a quadratic function instead of linear function in the linear program cases.